So I want to test the spatial autocorrelation in the July COVID-19 rates in Ottawa. And so I've downloaded some data for that, and you'll see these links as well in the exercise for yourself. And here I have the ONS map COVID _en.csv file. And then I also have the neighborhoods file. And you'll see the link as well in the exercise. So I'm just using this example instead of any of the ones in the slides or the exercise to show you how to do that. So first what I'm going to do is I'm just going to open up, copy that address as text, and I'm going to use my, just load my libraries up here. There we go. So all the libraries are loaded. Then I'll import my first one. I'll just call it Ottawa OTD here equals read.csv. And then I'll say literal quote. Inside those quotes, I'll put the path, COVID-19, and then the name of the file right here. Let's copy that, click on it, copy that over like so. I'll run that. So that's ready and okay. So I'm going to have a look at it. So I want to have a look at this particular data to see what's in there. So let's just say OTD. Oh, head maybe OTD. We'll get these along. You can see we have big names in there for the variables. So I'll just say names. These are the names of the variables in this data frame. Names OTD. Okay, so here they are. So we have, these are the names of the columns in that CSV file. We have this one, ONSID, but it's a I with an umlaut, ... ONS.ID. I don't know why they have that like that, but that's the Ottawa neighborhood study ID for the neighborhoods. There's also the neighborhood name. And then we have the following variables. Cumulative rate, excluding cases linked to outbreaks in long-term care homes. So we want to make sure when we're doing stuff, we're not including the long-term care homes because there's different processes that are involved in the neighborhoods and how that works in long-term care through outbreaks. So rate there. Then we have the rate per 100,000 population in October. Excluding cases, yeah, so that's one you look at. And you'll be looking at the cumulative one, which is the overall since the beginning of the pandemic. And you'll also be looking at the October one and the September one. So maybe I'll look at the August one. Or the July one. And we don't have anything earlier than that. That's available right now. So this is one of the variables I'll want to remember, and I can look up the names later. It's the 11th column in that table. So if I just looked at OTD, 11th column, that's that one there. And you see a lot of them are suppressed, because there's not enough, there wasn't enough people to, or there's too few people to report something. So those suppressed obviously will have to become no data. So we'll deal with that as well. So I want to make a simpler data table. So I'll just call it C rates for COVID rates. And I'll say that's going to be equal to CBIND. And then I want to make sure I have the neighborhood ID in there and the neighborhood name. So the first two from OTD. So I'll say OTD and then this and then that, columns 1:2. So it's just a vector of 1 and a 2 in it there. And then I want 11 as well. So I'll say OTD D 11, like so. but that's column. And I will also give this column a name because I don't want that giant name in there. Obviously, it's going to be difficult for me to type a 150 character name every time I want to refer to that variable. So I'll just call it COVID RT for rates, like so. I'll just run that line. And I'll just have a look at crates now. COVID rates. So we have our in there the names of the neighborhoods as well as the COVID rates for that was the July, I believe. And also get names of the COVID rates, C rates. Yeah, so we have the ONS ID, neighborhood name, and the COVID RT, so the COVID rate. Then I think I'm going to want to bring in my neighborhoods, so I'll just call those ONS for neighborhoods, ONS, Auto Neighborhood Study Neighborhoods, these are. And that's from that file, the shape file that's in that same folder, onsneighborhoods.shp. So here I'm going to use SF because I'm going to have to join tables and stuff, and that's much easier using SF. Remember, you did a lot with the SF package in the third exercise, I think it was, second or third exercise. And I'm going to use that here because it's both SP objects and SF objects are fine with SPDEP, which is the library we're using for spatial analysis of spatial autocorrelation. So I'll use the ST-read here. ST-read, and I'm going to grab the same thing from up here, same string literal, put it in here. Excuse me. Then it's going to be the shapefile, ONS neighborhoods. I think that's what it's called, ONS neighborhoods. Yeah. Obviously it's a file in Windows, so case sensitivity of the file doesn't matter. And it's not a CSV, it's an SHP file. Like so. So I'll just run that line. Okay, so that worked. We have 8 fields in there, 111 features, so 111 polygons in total. And it's a multi-polygon geometry type. And then our coordinate system is long lat, so I'm going to want to transform that. So again, this is easier. This is easy enough in this, so I'll just call this ONS again. And I'll say ST transform. And then ONS will go in there, and then my EPSG code, which is 32189 for an MTM9. MTM9 WGS84 in Ottawa. So I'll also run that. I'll just check my ONS again. Oop, not IBS, ONS. Let's just see. So just give me all the stuff there. ST transform. Simple feature. There it is. Simple feature collection. CRS net 83 MTM zone 9. That's good enough for what we're doing at 83 WGS84, the same thing today within a centimeter. So that'll be just fine. And then we have in here, just showing the first 10 features now in there for this transformed one. And we got FID flag, and we have an ONS ID. That's what we need to know that, because that'll match up with the other ONS ID in the CSV table when we join them together. So I need to now bring in to the table for ONS, which is the geometry. Maybe I'll just plot that quickly to show you. I'll just say, okay, let's have a look at that. The ONS file itself. So I'll just call this ONS layer equals TM dot shape, of course, TM shape, and that will be ONS, and plus it'll be polygon plus TM polygon, like so. And I won't give it any, just default fill here, and I'll print that. Print the ONS and LOIR here. There we go. So that's the ONS neighborhoods in the MTM9 projection, so that everything looks good there. So now what I want to do then is by the neighborhood ID. So if I look at my ONS over here, ONS $, ONS ID right there, looks like that. And then in my C rates, $ ONS ID is right there. And they're not sorted in the same way. One is sorted numerically. There's 111 in each. So this is my unique identifier, how I can join data about the COVID-19 rates that's in C rates, the July one. I can join that to the spatial data table for ONS, because the ONS spatial data table has what in it. So if I say names, ONS, it only has FID, flag, ONS ID, name, population estimate. So there's a pop estimate in there. Then more name stuff and a shape area, shape length, and geometry field. So obviously it doesn't have any information about COVID-19 in the neighborhoods as it stands right now. So I'll have to do a join. And the way to do that is, again, because we're using the ST or the SF library, I can just use left join. So I'll call what should I call this here? J for now. J equals left join. And then in here, what do I want to join to what? Well, I want my ONS joined to C rates. So COVID rates. And I want it to be by the ID. So left join here means that I'm joining crates, C rates, that information to the left input, which is ONS. That's all that means, left join. And it'll keep everything in ONS, even if there's not a matching item in C rates, for example. And okay, so by equals C, and then we have ONS ID, which is in ONS, and that'll be equal to, what's the name of the one in the other one? I have to go over here. Names again of crates. And it's this one, so I'm just going to copy that. Like so. So I'll run that. That should work. Now, if I say names of J, so J is now the same thing that you see here is ONS, except it has now the COVID rate in there as well. And it is of, if I just say J here, J is just an SF object. So spatial polygons, a multi-polygon object of SF. So it has everything in there I need. So now I've joined that data. So let's just check it out. I'll say head J. But see here, it says the COVID RT up here still says like suppressed. I need to convert those to NAs. Because right now, if I just get that out of there, if I say J $ COV rate RT, it's characters. So I need to make those into numerics. So I need to do that next, or I actually probably be easier to do it up here before I did when I first brought it in. So I said as.numeric that field, which remember it's the 11th field in the OTD table, the original CSV. Like so. So I use as numeric on a character column, because notice this character column also has numbers in it. And so what it will do is, for things that aren't numbers, it'll convert them to NA, no data. Things that are numbers, it will convert it from take the quotes away and make it a number. And so yeah, I'll do that up here. I'll just remake this one crates here. I'll just select all of them down to the left join and just redo those ones. I did see a warning message up here. Okay, crates, warning message, data frame, check names false, NA induced by coercion. Okay, that's fine. That just means what I said before. It couldn't coerce the word suppressed into a number, so it made it an NA. So if I check that now, back on J here, J $, the COV rates. Good, so now we have a numeric one with NAs where there's no data, and values in terms of number of people per 100,000, the rates. Now I want to get, because in order to do the spatial autocorrelation analysis, I can't have a whole bunch of NAs. I can only use non-NA data for analysis of spatial autocorrelation. So I have to get I have to subset out of J right now, which is all the neighborhoods, just the ones that have values for the number of infections per 100,000. So I'll go down here and I'll just do that with a subsetting, just regular type of subsetting. I'll say J equals J, such that not is .NA J $COV dirt, comma, like so. So again, I'm using the is.NA to figure out which of the values in the COV rate, COVID rate, right here that we see in this part, which of those values are NA, and that'll create a vector that's true or false. True if it's NA, false otherwise. And then I invert that by saying not is.NA. So all of the falses, where the numbers are, will become true. All of the NAs will become falses. And so it will only take over what is true. And I need to put a comma here. There we go. And put it back in J. So I'll run that. Argument 2 is empty. What do you mean? Oh no, I don't need one there. What's going on there? Oh, I have a comma in there for some reason, which I don't need. There we go. I'll run that again. J. So J now, if I just look at J $COV RT, see, I only have the numbers here. Each represents a polygon where the COVID rate was positive in July. So I probably want to have a look at that. So I'll make a J layer, JLYR equals TM shape, and I'll say this will be the J plus, I'll do a TM polygons, column equals COVID RT. I'll put a quote around that. Yep. Quote, but I don't want to keep the ones here. So let's be by default natural breaks, I guess, TM polygons on the COVID rate. Then I'll print that. So, okay, so here we go. That's what it looks like right now. So in July, of course, that was at the bottom of the, or the bottom of the curve, so to speak. Here we have light colors, and then we have a couple darker ones in this region over here. So we'll have to see what we can find out next. The next thing that we do is we create a adjacency matrix based on this. So I'm going to call that just NB and NB, and that'll be poly 2NB. And what we want in there is J. And I'll use, that should be good. Yeah, just poly 2NB. By default, it's Queen's case, so that's fine. So I'll just run that. Now I have to look at that NB. So I'll look at my neighbors object, and look at here. It says, for example, 7 regions have no links. So we can't undertake a spatial autocorrelation when we have something like 7 regions with no links, and that makes sense here, right? If we look at that on there, so let's say I want to put that on there as well. I'll just go back here and make another layer after I made the poly 2NB. And to plot the neighborhood graph on top of that so we can see the connectivity, I'm going to have to create another TM shape. So I'll call this NBLYR equals TM shape. And then I can't use a neighborhood object like that directly because it's not a SF object. So it has to be converted to an SF or SP object. And I think there's the command to do that is NB2 lines. Yeah, NB2 lines NB, and then chords equals ST geometry of J. Let's see if that'll work. Okay. So shape, and then I have to say plus here, TM lines, like so. Okay. So that should, let's see if that'll run plot. So I'll then print my polygons first, JLYR, and plus NBLYR. So let's run those and see what happens. There we go. So now we can see the neighbor graph on top and what's connected to what. And I'm just making it a little bit bigger here to see. So we can see obviously where the connections are where things are adjacent to each other. But then we have some things where there's no lines going to. So that polygon here, this polygon, these 2 polygons, that one over here, and this one. So obviously we can't use poly 2NB as a means to get an adjacency matrix, a full adjacency matrix for these things. So instead, maybe we'll use a we'll use a nearest neighbor definition of adjacency. And the first thing I want to get is the centroids, since the centroids will be used to create the neighborhood matrix, the adjacency matrix. So I'll just call that what do we call that? J chords equals, again, ST, and we'll use centroid here. So this is made for that. And then the geometry, J. And then we'll say of largest polygon equals true. I'll put that in a separate line. And that just means that if there's a multi-part polygon, which there may be in this case, to put the centroid within the largest part of that multi-part polygon. So J-chords will hold those centroids that I can then use to do a k nearest neighbor. So I'll just run that. Oh, Control Z, Control run. There we go. So J-chords looks like that. So it's a point SF object. Then I'll make something called aught.knn for knn, where k is going to be equal to the four nearest neighbors for each polygon. So adjacency will now be based on the four nearest neighbors instead of just sharing a border, since we have islands everywhere. We can't use regular adjacency to test this stuff out. So to start with that, I use the k near nay, k near nay. That's what it's called, k near nay. And in here, I'm going to put my J chords, and then what number, k equals 4. So 4 nearest neighbors. Hit enter. And then I convert that to a neighborhood matrix, and I'll just call it NB equals, it'll be KNN to NB. So other ones to NB, this is KNN to NB. And that'll be aught KNN, and I'll just run that. There we go. Now let's have a look at that neighbors. So I'll just look at NB. Okay, so no non-zero links. So great. We don't have any problems with that. I'll check summary of NB. And I might have to make that a little bit smaller here. So with the summary of NB, like that, I can see my distribution list. So I have 25 least connected regions have 4 links, and 25 most connected regions have 4 links, of course, because we asked for 4, right? So 25, there's 25 regions, and each has 4 links, just to double check that everything worked there the way we wanted to. I'll just re-expand the box there so we can show now the neighborhood on top of there instead. So I will again convert that. I'll just copy I think I had the code already up here. Yeah, so I'll just copy this one here and just modify it for the new one here. NB2 lines NB. So still called it NB again, so that's fine. Coordinates to geometry J, yep. TM lines, so that's our new NBR layer. So I'll just run that. And then I'll print that one up there again. Great. So copy that down there, just so it looks, that's all I did, was run that sequence. Here we see then everything's connected to everything else now. Everything has 4 neighbors. And so that's how we have to deal with things when we have such sparse data like that, if we want to assess the spatial autocorrelation. Another option here could have been by distance as well, but by distance, it's possible we could have still missed some of the islands. So using the k nearest neighbor graph is probably the best idea here to test the spatial autocorrelation. So now I'll convert that to a weights matrix. So I'll say, what do I call this? WT, I guess, for weights equals NB2 list W. And then in here, the neighbors, which is NB. This is the K and N, nearest neighbors. Style is by default W, but I'll put it in anyway. STYLE equals W. Instead of binary, because we're working with continuous data now. So we want that row standardization to happen, so that although here, since they all have the same number of neighbors, it probably doesn't matter too much whether it's W or B, but just for form, we'll put W. And zero policy is true. To make sure that if, for example, there is a missing link somewhere, it'll give an error and fail. So I'll just run that line. So now we have everything we need to do a spatial autocorrelation test. And that spatial autocorrelation test will be Moran's, I'll just make some space here, moran.mc, and I'll just save it. So this will be July.moran equals moran.mc. And in here will be the variable that I want, j cov rate. So j COVID rate. And then the WT, which is our weights, and zero policy to true. And by default, this is going to be testing for positive spatial autocorrelation because greater is the default. So I'll just run it. And I forgot to put nsim, of course. That's fairly important. And I'll put nsim equals 999. There we go. And it's finished very quickly. I'll maybe put that on a couple lines so it's easier to see on the screen here. So now I'll have a look at the results, July.moran. So what it says here is that the p-value is 0.61. And so there is no evidence, no strong evidence to reject the null hypothesis that the distribution of COVID rates in July are anything but randomly put in space, basically. So we have very little evidence. We could look at the alternative the other way. So the other alternative, right, is negative spatial autocorrelation. The p-value in this case will probably just be more or less 1 minus 0.61. But we'll try it anyway, the other direction. So I'll say, I'll just stick in here the argument alternative equals less, like so. I'll run it now. And we'll check that again, July.moran. So it's 0.385, which is around, the other one was 0.61, 1 minus 0.61, 0.39, 0.385, rounded up, same thing. So basically there's no positive, there's no negative significant autocorrelation, there's zero spatial autocorrelation. But what if we had changed? What if we now want to test that again? What if maybe we just chose too many neighbors, because these distances are pretty far for some of them. So what if I change my neighbors to 3? Well, I can just go back up here to where it says k equals 4, put k equals 3, and then just run all the lines after that, like so. And then check out what it says. Same thing, still not significant. And that was again for lesser, and greater would just be again 1 minus that. So 0.6 or 0.7 through 4. So you can quickly change, what the assumptions are like. What if it's k equals 5 neighbors? Well, try it again. And I'll put the alternative back to greater. Most commonly, that's what's looked for. And enter again. And here we go. So obviously more lines on the graph now. And if I say July.moran, which is the result of the Monte Carlo simulation, still not significant. And this is just to give me some confidence, at least, that my choice of neighbors, 3 versus 4 versus 5, still provide the same result, something that is non-significant. And so that gives me more confidence that this is really a non-significant result in this case. And so that's how we can undertake that, for at least for July anyway. So for the July uh, data, that didn't work out. And then, changing it for another data set in there, just changing that line up here and rerunning the whole thing. Pretty straightforward.